Scattered across our galaxy, there exist objects so dense that a teaspoon of their material would weigh more than Mount Everest, objects where gravity becomes so intense that time itself slows to a crawl. Near the surface of these neutron stars, the most extreme objects in the universe short of black holes, gravitational fields reach strengths billions of times stronger than Earth's. At such extremes, 1 second measured by a clock hovering just above the neutron star's surface corresponds to roughly 1,000 years, passing on Earth a time dilation so severe that it transforms our understanding of what time means. We thought we understood time as flowing uniformly throughout the universe. We built our physics and daily lives around the assumption that a second is a second whether measured in New York, on Mars, or near the most massive stars. Every clock properly synchronized should tick at the same rate, marking the passage of time as an absolute cosmic metronome against which all events occur. We were profoundly mistaken. Einstein's general theory of relativity, confirmed through countless experiments from atomic clocks on aircraft to GPS satellite corrections, demonstrates that time flows at different rates depending on gravitational field strength. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields when compared by distant observers. This gravitational time dilation, barely noticeable in Earth's modest gravity, becomes dramatic near neutron stars, where gravitational fields reach such intensity that space-time curvature approaches the theoretical maximum possible without forming a black hole. At the surface of a typical neutron star with mass approximately 1.4 times the Sun's mass compressed into a sphere merely 20 kilometers in diameter, the gravitational field strength reaches approximately 2 x 1012 meters per second squared, roughly 200 billion times stronger than Earth's surface gravity. This creates a gravitational potential so deep that time dilation factors approach 0.7, meaning clocks at the neutron star surface run at about 70% the rate of distant clocks. But the extreme scenario mentioned in the title requires venturing even closer to the theoretical limits. For the most massive neutron stars approaching 2 solar masses compressed to minimum stable radii near 10 to 11 kilometers, the surface sits precariously close to the Schwarzschild radius, where black hole formation would occur. At these extremes, gravitational time dilation can theoretically reach factors where 1 second at the surface corresponds to hundreds or even thousands of years measured far from the star. The physics underlying this extreme time dilation follows directly from general relativity's geometric description of gravity. Mass curves, spacetime, and clocks measure proper time along paths through this curved geometry. Different paths between the same spacetime events correspond to different elapsed proper times. Near neutron stars, where spacetime curvature becomes extreme, proper time intervals at the surface become dramatically shorter than coordinate time intervals measured by distant observers. Dr. Saul Tucholsky, whose theoretical work on relativistic astrophysics has mapped the behavior of matter and radiation in extreme gravitational fields, emphasized that neutron stars provide natural laboratories for testing general relativity in regimes impossible to access through any other means. The time dilation near these objects isn't speculation, but direct consequence of well-tested theory describing observed phenomena, including pulsar timing, gravitational wave signals from neutron star mergers, and X-ray emission from accreting systems. This exploration will take us from the formation and properties of neutron stars through the foundations of gravitational time dilation, from the mathematics describing extreme time warping to thought experiments with observers experiencing vastly different time rates. We'll examine how measurements confirm these predictions, what happens to matter and light in such intense gravity, and what the existence of these cosmic time machines reveals about the fundamental nature of time and space-time. If you're fascinated by physics, predicting that time can slow, by factors of thousands while remaining perfectly consistent with observation and experiment, subscribe and give this video a thumbs up. And consider this: if time flows at radically different rates at different positions in a gravitational field, what does that tell us about whether the past and future exist objectively, or whether time is merely a coordinate whose meaning depends entirely on one's location in curved spacetime? Comment your thoughts. I'll pin the most insightful response. For most of human history, time seemed obviously universal and absolute. The sun rose and set with regular periodicity. Mechanical clocks ticked at steady rates. All measurements suggested that time flowed uniformly everywhere, providing a cosmic backdrop against which events occurred in definite sequence. Newton formalized this intuition, declaring that absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. This Newtonian framework worked brilliantly for describing terrestrial motion, planetary orbits, and essentially all accessible phenomena through the 19th century. No observation demanded reconsidering time's absolute nature. The idea that clocks might tick at different rates, depending on gravity or motion, seemed absurd. How could time itself change when it represents the very measure by which change occurs? Einstein's special relativity in 1905 first challenged absolute time by showing that observers in relative motion measured different time intervals between the same events. Moving clocks run slow. The faster the motion, the greater the time dilation. This velocity-based time dilation, while strange, applied only to objects moving at substantial fractions of light speed and left gravity untouched. General relativity, completed in 1915, revealed that gravitational fields themselves cause time dilation entirely separate from motion effects. Clocks in stronger gravitational fields run slower than clocks in weaker fields, an effect that becomes dramatic near compact objects like neutron stars, where gravitational field strengths reach billions of times stronger than anything experienced on Earth. The discovery of neutron stars began with theoretical predictions in the 1930s following the discovery of the neutron. Physicists Walter Baade and Fritz Zwicky proposed that stellar core collapse during supernovae might create objects supported by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to compression arising from the Pauli exclusion principle. These objects would possess masses comparable to the Sun compressed into radii of mere kilometers. The first observational evidence came in 1967 when Jocelyn Bell and Anthony Hewish detected radio pulses arriving with extraordinary regularity every 137 seconds from a source in the constellation Vulpecula. Initially dubbed LGM-1 for Little Green Men, due to the signal's artificial seeming precision, the source was soon understood as a rotating neutron star, a pulsar, sweeping a beam of radio emission across Earth like a cosmic lighthouse. The discovery of pulsars confirmed neutron star existence and provided laboratories for testing general relativity. Pulsar timing, measuring pulse arrival times to microsecond precision over years or decades, reveals subtle effects including gravitational time dilation, orbital decay from gravitational radiation, and space-time curvature near the neutron star surface. Three major revelations emerge from studying neutron stars and their extreme time dilation. First, these objects exist throughout the galaxy in numbers reaching millions, providing accessible examples of physics at the extreme where general relativity's predictions diverge dramatically from Newtonian gravity. Second, the time dilation near neutron stars has been measured through pulsar timing and gravitational wave observations, confirming theoretical predictions to remarkable precision. Third, the existence of neutron stars approaching theoretical maximum masses creates conditions where time dilation reaches factors of hundreds to thousands, representing the most extreme time warping possible in the universe short of black hole event horizons. Now let's begin by establishing what neutron stars are, how they form, and what makes them the densest objects in the universe capable of existing stably without collapsing into black holes. Neutron star formation. Neutron stars form during the catastrophic death of massive stars in supernova explosions when stellar cores collapse to nuclear densities and rebound, blasting outer layers into space while leaving behind ultra-dense remnants supported by neutron degeneracy pressure. Understanding neutron star formation requires examining stellar evolution, core collapse physics, and the quantum mechanics, preventing complete gravitational collapse to singularities. Massive stars with initial masses exceeding approximately 8 solar masses evolve through successive nuclear burning stages, fusing hydrogen to helium, helium to carbon and oxygen, and continuing through neon, oxygen, and silicon burning to build iron peak elements in their cores. Each burning stage produces less energy than the previous one and lasts for shorter durations as the star exhausts progressively heavier nuclear fuel. Iron represents the endpoint of exothermic fusion. Fusing iron into heavier elements requires energy input rather than releasing energy, making further fusion energetically unfavorable. When the stellar core converts to iron peak elements, primarily iron 56 and nickel 56, no additional nuclear burning can generate pressure to support the star against gravitational collapse. The core becomes mechanically unstable despite temperatures reaching billions of degrees. The core collapse begins when iron photodisintegration removes energy by breaking iron nuclei back into helium nuclei and free protons, absorbing photon energy and reducing thermal pressure. Simultaneously, electron capture onto protons produces neutrons and neutrinos, removing electrons that previously provided degeneracy pressure support. The core implodes catastrophically, reaching infall velocities exceeding 70,000 kilometers per second, nearly 1/4 light speed. During collapse, density increases dramatically as matter compresses from typical stellar core density, around 10 kilograms per cubic meter, to nuclear density approximately 4 TeX 1017 ked M3, where nucleons pack as tightly as in atomic nuclei. At these densities, matter consists primarily of neutrons with smaller fractions of protons, electrons, and exotic particles. The equation of state, relating pressure to density, stiffens dramatically as nuclear forces become repulsive at short distances. The stiffening equation of state halts collapse when the core reaches approximately 1.4 solar masses compressed into radius roughly 10 to 15 kilometers. Nuclear forces and neutron degeneracy pressure, the quantum mechanical resistance of neutrons to occupying the same quantum state, finally balance gravitational compression. The collapse halts abruptly and reverses, creating an outward-moving shock wave that propagates through infalling material. This bounce shock initially stalls as it loses energy dissociating iron nuclei and pushing against continuing infall. However, enormous neutrino fluxes generated in the hot proto-neutron star core deposit energy behind the shock, reviving it after approximately 100 to 500 milliseconds. The revived shock accelerates outward, reaching the stellar surface in hours and ejecting several solar masses of material at velocities exceeding 10,000 kilometers per second. The explosion becomes visible as a supernova, briefly outshining entire galaxies and enriching the interstellar medium with heavy elements synthesized during the star's life and during the explosion itself. Elements heavier than iron, including gold, platinum, uranium, and others, form through rapid neutron capture processes in the extreme conditions during collapse and explosion. Left behind at the core, the proto-neutron star contains approximately 1.4 solar masses compressed initially into radius about 50 kilometers. Over the next tens of seconds, the proto-neutron star contracts further as it cools through neutrino emission, settling into a stable configuration with radius approximately 10 to 12 kilometers. This final object represents the neutron star, among the densest stable objects possible in the universe. Neutron star masses span a relatively narrow range from approximately 1.2 to perhaps 2.3 solar masses, based on current observations and theoretical constraints. The lower mass limit arises because core collapse-producing objects below approximately 1.2 solar masses might not proceed through iron core collapse, but rather through different mechanisms producing white dwarfs. The upper mass limit, called the maximum neutron star mass or Tolman-Oppenheimer-Volkoff (TOV) limit, depends on the equation of state of ultradense matter. Theoretical calculations predict maximum neutron star masses between approximately 2.0 and 2.5 solar masses, depending on poorly constrained properties of nuclear matter at extreme densities. Neutron stars more massive than this limit cannot support themselves against gravity, even with maximum neutron degeneracy pressure and nuclear force repulsion. Such objects collapse further, forming black holes where no known force prevents complete collapse to singularities. The heaviest confirmed neutron stars discovered to date possess masses near 2.0 solar masses. PSR J0348.0432, a millisecond pulsar in a binary system, has mass 2.01 plus 0.04 solar masses measured through relativistic orbital effects. PSR J0740.620 shows mass 2.14 plus 0.09 solar masses from Shapiro time delay measurements. These massive examples approach theoretical limits, providing crucial tests of dense matter physics. The radius of neutron stars depends on mass and equation of state. Typical neutron stars with 1.4 solar masses possess radii approximately 11 to 13 kilometers, based on recent observations from NICER X-ray telescope measurements and gravitational wave detections of merging neutron stars. More massive neutron stars might have slightly smaller radii near 10 to 11 kilometers, as additional mass compresses the star further toward the maximum density sustainable before black hole formation. The extreme density means that a cubic centimeter of neutron star material, roughly the size of a sugar cube, would weigh approximately 400 million metric tons, more than all humans on Earth combined. A teaspoon of this material would weigh roughly 10 million tons, comparable to Mount Everest's total mass. These density values exceed those in atomic nuclei, representing matter compressed to fundamental limits set by nuclear forces and quantum mechanics. Neutron star interiors possess complex structure with distinct layers. The outermost layer, the atmosphere, extends only centimeters thick but contains normal matter, including iron and lighter elements. Below this, the outer crust consists of atomic nuclei, primarily iron initially, but transitioning to increasingly neutron-rich nuclei with depth, embedded in a degenerate electron gas. At densities exceeding approximately 4 x 1011 kg M3, roughly 1,000th nuclear density, neutrons begin dripping out of nuclei, creating a neutron fluid permeating the lattice of nuclei. This marks the boundary to the inner crust, where nuclear pasta phases might form. Exotic nuclear matter configurations, including rod-like and slab-like structures created by competition between nuclear attraction and Coulomb repulsion. The crust-core boundary occurs at approximately half nuclear saturation density near 1.4 T 1017 kg M3. Below this, nuclei dissolve completely into uniform nuclear fluid, consisting primarily of neutrons with approximately 5% protons and electrons maintaining charge neutrality. This outer core liquid behaves as superfluid, with neutrons forming Cooper pairs and flowing without viscosity. The inner core, above approximately 2 to 3 times nuclear saturation density, remains highly uncertain. Possible exotic matter phases include hyperons, particles containing strange quarks, Bose-Einstein condensates of pions or kaons, or deconfined quark matter, where nucleons dissolve into their constituent quarks. The equation of state softens or stiffens depending on which exotic phases appear. affecting maximum mass and radius relationships. At the very center of the most massive neutron stars, densities might reach 10 times nuclear saturation density or higher. Whether such densities create quark cores, strange matter, or other exotic states remains unknown. These uncertainties represent one of the major unsolved problems in nuclear physics, determining matter's behavior at densities and pressures impossible to recreate in terrestrial laboratories. The formation of neutron stars in core collapse supernovae represents one of the most violent processes in the universe, converting gravitational potential energy exceeding 1046 joules, roughly 10% of a solar mass's rest mass energy, into neutrinos, kinetic energy of explosion, and gravitational waves. The extreme conditions during formation and the resulting ultra-dense objects create natural laboratories for physics at energies and densities beyond reach of any conceivable experiment. Understanding neutron star formation establishes these objects as stellar endpoints, where gravity compresses matter to nuclear densities, creating configurations where gravitational fields become billions of times stronger than Earth's, and where relativistic effects including dramatic time dilation emerge not as subtle corrections, but as dominant features determining physical behavior. Extreme properties. Neutron stars possess physical properties so extreme that they challenge intuition built from everyday experience with terrestrial matter and Earth's weak gravitational field. The combination of solar mass objects compressed to city-sized radii creates surface gravities, magnetic fields, rotation rates, and densities unlike anything else in the universe except black holes. Understanding these extreme properties establishes the context for the dramatic time dilation occurring in neutron star gravitational fields. Surface gravity at neutron star surfaces reaches approximately g Tolkien gm r2, where g represents Newton's gravitational constant, m the neutron star mass, and r its radius. For a typical 1.4 solar mass neutron star with radius 12 kilometers, surface gravity equals approximately 2x 1012 s2, roughly 200 billion times Earth's surface gravity of 9.8 s2. An object dropped from 1 meter height would strike the surface in approximately 1 microsecond at impact velocity exceeding 1,000 kilometers per second. This extreme gravity creates enormous differences in gravitational potential across small distances. The gravitational potential difference between standing on the neutron star surface and hovering 1 meter above equals df gdh, 2x 1012 joules per kilogram. This energy difference exceeds the rest mass energy of electrons, approximately 8x 1013 joules per kilogram, by only 2 orders of magnitude, indicating that gravitational binding energy approaches rest mass energy, a regime where general relativistic effects become essential. The escape velocity from neutron star surfaces, the minimum velocity needed to escape to infinity, equals approximately v or esk tidrash 2gmr 0.5 c to 0.7 c, where c represents light speed. This means escaping requires reaching velocities between 150,000 and 210,000 kilometers per second, 1/2 to 2/3 the speed of light. Photons emitted from the surface lose substantial energy climbing out of this deep gravitational well, emerging with gravitational redshift factors approaching 1.3 to 1.5 for typical neutron stars. The gravitational binding energy of a neutron star, the energy required to disassemble it against gravity, equals approximately 0.1 to 0.2 times the rest mass energy, mk2. For a 1.4 solar mass neutron star, this represents roughly 0.15, 1.4, 2x 1030 kilo, 3x 100 mem s2, 4x 1046 joules. This enormous energy reservoir powers supernovae, with most released as neutrinos during the proto-neutron star's initial cooling. Magnetic field strengths at neutron star surfaces span an enormous range from approximately 108 Tesla for millisecond pulsars to 10 to 11 Tesla for magnetars, the most strongly magnetized objects known in the universe. For comparison, Earth's surface magnetic field reaches about 5 × 10⁵ Tesla, while the strongest sustained laboratory fields approach 100 Tesla. Neutron star fields exceed laboratory capabilities by factors of millions to billions. These ultra-strong magnetic fields arise from conservation of magnetic flux during core collapse. The progenitor star's magnetic field, threading through the core region that collapses, becomes compressed as radius shrinks from tens of thousands of kilometers to 10 kilometers. The magnetic field strength scales approximately as B1R2, amplifying modest stellar fields of 0.001 to 1 Tesla to neutron star values exceeding 108 Tesla through the million-fold compression. Rotation rates span from seconds per rotation for young pulsars to milliseconds for millisecond pulsars spun up through accretion from companion stars. The fastest confirmed pulsar, PSR J17482446A, rotates 716 times per second with equatorial velocity reaching approximately 0.24 c or 24% light speed. At these rotation rates, the centrifugal acceleration at the equator reaches substantial fractions of gravitational acceleration, and frame dragging effects from general relativity become important. The rotation rate limits arise from mass shedding at the equator when centrifugal forces overcome gravity, and from gravitational wave emission from non-axis symmetric distortions. For typical neutron star masses and radii, the maximum rotation rate before mass shedding occurs reaches approximately 1,000 to 2,000 rotations per second. Observed pulsars remain well below this limit, suggesting either they don't reach maximum spin during formation or that gravitational wave emission and magnetic braking limit rotation rates. The moment of inertia for neutron stars, relating angular momentum to rotation rate, equals approximately E2 to 5 mR2, modified by relativistic corrections and equation of state effects. Date: for a 1.4 solar mass, 12-kilometer radius neutron star, the moment of inertia reaches approximately I 1.3 x 1038 Camturi. The rotational kinetic energy of a millisecond pulsar equals E rot Orks 1.2 I2 1042 to 1043 joules, comparable to total solar output over its entire main sequence lifetime. The rotational flattening, the difference between equatorial and polar radii due to centrifugal effects, remains modest even for rapidly rotating neutron stars. For a 7 to 16 Hz pulsar, the equatorial radius exceeds the polar radius by only approximately 10%, far less than the dramatic flattening of Jupiter or Saturn. This reflects the extremely strong gravitational binding that resists centrifugal distortion. Temperature distributions across neutron star surfaces show substantial variations driven by magnetic field geometry and heat transport. Young neutron stars born in supernovae emerge with core temperatures exceeding 10 to 11 Kelvin, but cool rapidly through neutrino emission over seconds to minutes. After approximately 100 years, surface temperatures drop to roughly 106 Kelvin, emitting primarily X-rays. After millions of years, cooling continues to approximately 105 Kelvin as the star radiates thermal energy away. The thermal conductivity of neutron star crusts affects temperature gradients between core and surface. Lattice vibrations and electron scattering determine heat transport rates. Superfluidity in the core, where neutrons form Cooper pairs below critical temperature, affects neutrino emission and cooling rates through suppression of certain neutrino production channels. Starquakes occasionally crack neutron star crusts as the star's rotation slows and centrifugal support decreases, causing the crust to settle to smaller radius. These quakes release energy reaching 1039 to 1041 joules, comparable to all solar output for thousands of years, creating sudden spin-up glitches observed in pulsar timing, where rotation rate jumps suddenly before gradually returning to normal spin-down behavior. The equation of state relating pressure to density determines neutron star structure through the Tolman-Oppenheimer-Volkoff equations, the general relativistic generalization of hydrostatic equilibrium. Different equations of state predict different mass-radius relationships and maximum masses. Current constraints from NICER X-ray observations, measuring pulsar radii and gravitational wave observations of merging neutron stars, narrow allowed equation of state parameters, but haven't yet uniquely determined the form. Exotic matter phases potentially present in neutron star cores include hyperons containing strange quarks with strangeness S, Chakrul 1, 2, or 3. The appearance of hyperons softens the equation of state, reducing maximum mass and potentially creating problems reconciling models with observed 2 solar mass neutron stars. Pion or kaon condensates represent another possibility, where these mesons form coherent quantum states reducing pressure. Quark matter phases, where nuclear matter dissolves into constituent up, down, and strange quarks, might exist in the densest neutron star cores. If the transition from hadronic to quark matter occurs in stable configuration, hybrid stars containing both hadronic and quark matter regions could exist. If quark matter becomes energetically favorable at all densities, strange quark stars consisting entirely of deconfined quarks would represent a different class of compact objects. Color superconductivity in quark matter, where quarks form Cooper pairs analogous to electron pairing in conventional superconductors, affects the equation of state and transport properties. Various color superconducting phases with different quark pairing patterns might exist depending on density and temperature, creating rich phase diagrams for dense quark matter. The observational signatures of different interior compositions include radius measurements, moment of inertia, determinations from binary pulsar observations, tidal deformability constraints from gravitational wave observations, and cooling curves tracking temperature evolution over time. The NICER telescope measurements of pulsars PSR J-030 plus 0451 and PSR J-40 plus 6620 constrained radii to approximately 12 to 13 kilometers for masses around 1.4 solar masses, favoring relatively stiff equations of state without dramatic softening from exotic matter. Gravitational wave observations of the binary neutron star merger GW17 A17 constrained tidal deformability, the degree to which neutron stars distort in binary companions' gravitational field. The measurements favored stiff equations of state and set upper limits on neutron star radii around 13 kilometers for 1.4 solar mass stars. Combined with NICER results, these observations narrow the range of viable equations of state substantially. Understanding neutron stars' extreme properties establishes why these objects create the conditions for dramatic gravitational time dilation. The combination of solar masses compressed to kilometer radii creates gravitational potentials so deep that relativistic effects dominate, warping space-time sufficiently that time itself flows at radically different rates at different positions relative to the star. Gravitational time dilation. Mathematics. The quantitative description of gravitational time dilation near neutron stars emerges from general relativity's metric solutions, describing curved spacetime around spherically symmetric masses. Understanding the mathematics reveals why time slows near neutron stars and enables calculating exact time dilation factors for various positions and neutron star configurations, including the extreme cases where 1 second at the surface corresponds to centuries or millennia far from the star. The Schwarzschild metric describes space-time geometry outside a spherically symmetric, non-rotating mass m. In Schwarzschild coordinates T, R, F, the metric takes the form ds2, 1rsr, c2dt2 plus 1rsr, 1dr2 plus r2 dθ2 plus sin2 saf df2, where rs r2gmc2 represents the Schwarzschild radius, the radius of the event horizon, if all mass m were compressed into a black hole. For a 1.4 solar mass object, r/s 4.1 kilometers. Neutron star radii typically exceed r/s by factors of 2.5 to 3, placing their surfaces outside the event horizon, but in regions of extreme spacetime curvature. The proper time dt measured by a clock at fixed position, constant r, f, relates to coordinate time dt through the metric component g(t)(t)(1) rtgs(r). For an observer at rest at radius r, the relationship becomes dt(1) rts(r) dt. This shows that proper time intervals dt measured locally equal coordinate time intervals dt reduced by the factor 1 rts(r). As r approaches ris, this factor approaches 0. Proper time intervals become infinitesimal compared to coordinate time intervals measured by distant observers at IR, where the factor equals unity. The time dilation factor, the ratio of proper time to coordinate time, equals x(dt)(dt) 1 rts r 1 2gm rc2. For positions far from the star where A approaches 1 and time dilation becomes negligible. For positions near the Schwarzschild radius where r approaches ris, A approaches 0 and time dilation becomes extreme. For a typical neutron star with m, or 1.4 m, in approximately 2.8 x 1030 kilos, and radius r ever 12 km, the time dilation factor at the surface equals A bar 126.67 x 1011 2.8 sig 1030 12 s103 9 sat 1016 A bar 1373 sat 20 108 out 1021 A bar 10345 A bar 655 0809. This means a clock at the surface runs at approximately 81% the rate of distant clocks. 1 hour at the surface corresponds to approximately 1.24 hours of coordinate time, or roughly 1 hour 14 minutes. The time dilation, while substantial, falls far short of the 1 second or 1,000 years extreme mentioned in the title. To achieve time dilation factors where 1 second equals 1,000 years requires a 131,536,000, the number of seconds in a year divided by 1,000. This demands 1 RSR 3.17 x 10.8, squaring both sides 1 RSR 10.15, therefore RSR1 10.15 0.9 This requires RRS 1 plus 10.15, positioning the clock within approximately 10.15 times the Schwarzschild radius above the event horizon itself. For a 1.4 solar mass object with RS 4.1 kilometers, this places the clock at approximately R 4.1 kilometers, all 4 x 10 to 12 meters, within roughly 4 picometers of the event horizon. Such positioning is clearly impossible for neutron stars since their surfaces lie at approximately 12 kilometers, far outside the Schwarzschild radius. However, for the most massive neutron stars approaching maximum mass, limits near 2 to 2.3 solar masses, and minimum stable radii, the surface approaches closer to the Schwarzschild radius, increasing time dilation substantially. For a maximum mass neutron star with M Falke 2.3, M 4.6 x 1030 kilos and minimum radius, R around 10 kilometers, values near theoretical limits. The Schwarzschild radius equals R Chas, R 2 GMC2, Task 2, Tax 0.67, Acom 10, 11, 4.6 x 1030, 9 x 1016, 6.8 kilometer. Time dilation factor at the surface becomes A TF 1 6.8 to 10, CR 0.32, 0.500 XC6. This represents time running at approximately 57% the distant rate, substantially slower than typical neutron stars but still nowhere near the extreme 1 second falls 1,000 years factor. 1 second at the surface corresponds to approximately 1.77 seconds distant time, or 1 year corresponds to roughly 1.77 years. To achieve extreme time dilation factors approaching 1000.1 requires considering hypothetical positions very close to the Schwarzschild radius, either unstable orbits just above the event horizon of a black hole, theoretical configurations at the absolute maximum mass limit, where neutron star surface radius exactly equals the Schwarzschild radius. Positions held stationary by external forces just above the surface of near maximum mass neutron stars. For practical neutron star cases with stable surfaces outside event horizons, realistic time dilation factors range from approximately 0.7 to 0.9, corresponding to surface clocks running 70% to 90% the rate of distant clocks. 1 year at the surface corresponds to approximately 1.1 to 1.4 years distant time, substantial but far from the thousands mentioned in the title. The coordinate time to proper time relationship becomes dt surface, T1 r/s r. For a 1.4 m neutron star with r, 12 km, 1 year, 315 x 107 seconds, at the surface corresponds to dt cam 3.15 x 107 0809 3.89 x 107 seconds, 1.24 years distant time. Title's claim of 1 second by 1,000 years represents the mathematical limiting case as surfaces approach event horizons, illustrating the principle that time dilation can become arbitrarily large as gravitational fields approach black hole strengths, even though practical neutron stars don't achieve such extreme factors. The gravitational redshift z of photons emitted from radius r and observed at infinity relates directly to time dilation through 1 plus z1 swan r/s-r. For the 1.4 m neutron star example, photons from the surface show redshift z1 0809 1.236, meaning wavelengths increase by approximately 24%. Visible red light at 650 nm becomes near-infrared at roughly 805 nm. For maximum mass configurations with a 0.566, redshifts reach Z0.77, shifting visible light well into the infrared. The Shapiro time delay, the additional time required for light to travel through curved spacetime near massive objects, provides another manifestation of gravitational effects. For light passing at minimum distance r$min from mass m, the extra time delay compared to flat spacetime equals dt 2gm c3 ln4r1r2 r min2, where r1 and r2 represent distances of emission and reception points from the mass. For pulsar signals passing near neutron star companions in binary systems, Shapiro delays reach microseconds to milliseconds depending on orbital geometry, allowing mass measurements through timing analysis. General relativistic orbital precession, the advance of periastron in binary systems beyond Newtonian predictions, equals dou Sigschran 6 pgm AC2 to 1e2, where A represents semi-major axis and as eccentricity. For tight pulsar binaries, precession rates reach several degrees per year, orders of magnitude larger than Mercury's famous 43 arcseconds per century precession that provided early general relativity confirmation. Understanding the mathematical framework establishes how time dilation varies with position in neutron star gravitational fields, and reveals that while practical neutron stars create substantial time dilation factors of 20% to 45%, achieving the extreme thousand-fold factors requires approaching event horizons of black holes or hypothetical maximum mass configurations at stability limits. Observational evidence. The gravitational time dilation near neutron stars, while predicted by general relativity, requires observational confirmation through measurements of actual neutron star systems. Multiple independent techniques including pulsar timing, gravitational wave observations, X-ray spectroscopy, and binary orbital dynamics provide compelling evidence that time indeed flows at different rates near these extreme objects, validating the theoretical predictions to remarkable precision. Pulsar timing represents the most precise technique for measuring relativistic effects near neutron stars. Pulsars emit beams of radio waves sweeping across space like lighthouse beams, creating pulses detected at Earth with extraordinary regularity. Millisecond pulsars, spun up to rotation periods of 1 to 10 milliseconds through accretion from companions, provide especially stable timing with pulse arrival time predictability approaching atomic clock precision. The timing model for a pulsar accounts for all known effects influencing pulse arrival times, including the pulsar's rotation rate and spin down, proper motion across the sky, parallax from Earth's orbital motion, and propagation effects through the interstellar medium. Deviations from simple models reveal additional physics, including binary orbital motion and general relativistic effects. Binary pulsars orbiting compact companions provide ideal laboratories for testing gravitational time dilation. The Hulse-Taylor binary pulsar PSR B1T-30 plus 16, discovered in 1974, contains a 59 millisecond pulsar orbiting a companion neutron star with 7.75-hour orbital period. The system shows multiple relativistic effects, including orbital decay from gravitational wave emission, gravitational redshift, and time dilation from orbital motion. The gravitational redshift and time dilation in the Hulse-Taylor system arise from two sources: the varying gravitational potential as the pulsar orbits in the companion's field, and velocity-based time dilation from the orbital motion. Both effects vary periodically with orbital phase, creating systematic pulse arrival time variations measurable through long-term timing. The time dilation amplitude in binary pulsars equals g by e ptb 2p 2 to the 3 gmc c 1 3, where e represents eccentricity, ptb orbital period, and mc companion mass in solar masses. For the Hulse-Taylor pulsar with e 0.617 pb 2797 seconds and mc 1.39 m, the time dilation parameter reaches GRE 4.3 milliseconds, creating measurable periodic variations in pulse arrival times. The double pulsar system PSR J07373039AB, discovered in 2003, provides even better tests by containing two pulsars visible from Earth, allowing observation of both neutron stars' rotations and relativistic effects. The system shows Shapiro time delay when one pulsar's signals pass through the companion's gravitational field, gravitational redshift differences between the two pulsars, and orbital precession at 17 degrees per year. Measurements of these effects determine system parameters, including component masses to 0.05% precision, MA, so 1.381 plus 0.007 m, and MB, 1.2489 plus 0.007 m pass. The observed relativistic effects match general relativity predictions to better than 0.05%, providing stringent tests of strong field gravity and confirming gravitational time dilation occurs at predicted rates. Gravitational wave observations of merging neutron stars directly detect time dilation through the gravitational wave signal's frequency evolution. The LIGO and Virgo detectors observed GW170817, a binary neutron star merger, at approximately 130 million light-years distance. The detected waveform showed frequency increasing from approximately 25 Hz to over 2000 Hz during the final seconds before merger, as the neutron stars spiraled together at increasing velocities while experiencing increasing gravitational fields. The orbital velocity at merger approached 30% light speed, creating velocity-based time dilation factors near 0.95. Simultaneously, the neutron stars approached to separations of tens of kilometers, where gravitational time dilation from each star's field became significant. The combination of effects appears in the gravitational waveform phase evolution, which must match general relativity predictions precisely for the merger to be properly characterized. Analysis of GW170817 confirmed that gravitational wave propagation speed equals light speed to within 1 part in 1015, validating a fundamental general relativity prediction. The observed signal matched numerical relativity simulations of merging neutron stars, including all relativistic effects to high precision, providing confidence that time dilation and other general relativistic phenomena operate as predicted in these extreme conditions. X-ray spectroscopy of accreting neutron stars measures gravitational redshift directly through atomic line emission from the neutron star surface or from accretion disk material very close to the star. The most precise measurements come from thermonuclear X-ray bursts, sudden brightening events from runaway helium fusion on accreting neutron star surfaces. During X-ray bursts, the neutron star photosphere expands briefly to larger radii as radiation pressure exceeds gravity. Spectroscopic observations detect absorption lines from iron and other elements in the photosphere. As the photosphere settles back down during burst decay, the absorption lines shift to longer wavelengths due to increasing gravitational redshift as the photosphere sinks into the deeper gravitational potential. Measurements of these redshift variations in sources including EXO 07486676 and GS 182624 yield gravitational redshift parameters zeta del L ranging from approximately 0.2 to 0.35, corresponding to MR ratios consistent with neutron star masses of 1.4 to 2 solar masses and radii of 10 to 13 kilometers. These measurements confirm substantial gravitational redshift and time dilation as predicted for neutron stars. The NASA X-ray telescope aboard the International Space Station makes precise measurements of pulsar pulse profiles across X-ray energies, constraining neutron star radii through detailed modeling of emission regions on the stellar surface. The pulse profile depends on the star's radius, mass, and emission geometry. General relativistic effects, including light bending and gravitational redshift, affect the observed profiles. NASA observations of millisecond pulsar PSR J0030+0451 yielded radius R as 12.71 plus 1.14 km for mass M as 1.34 plus 0.16 m as corresponding to gravitational redshift Z 0.23 and time dilation factor A 0.81. Observations of PSR J0740+620 with mass 2.14 plus 0.09 m. Constrained radius to 12.39 plus 1.30 kilometers, giving Z 0.35 and A 0.74. These measurements directly probe spacetime curvature near neutron star surfaces. The orbital period decay of binary pulsars through gravitational wave emission provides another test of general relativity. The Hulse-Taylor pulsar's orbital period decreases by 76 microseconds per year due to energy loss to gravitational waves, matching general relativity predictions to better than 0.2% after accounting for kinematic corrections from proper motion and galactic acceleration. This orbital decay demonstrates that gravitational waves carry energy from the system at rates general relativity predicts, indirectly confirming the theory's description of spacetime dynamics. Since time dilation follows from the same mathematical framework producing gravitational waves, the observed orbital decay strengthens confidence in time dilation predictions. Pulsar glitches, sudden jumps in rotation rate from starquakes cracking the neutron star crust, reveal interior structure through how the star responds to sudden perturbations. The post-glitch relaxation depends on how angular momentum transfers between the crust and superfluid interior, constraining interior properties. While not directly measuring time dilation, glitch observations confirm neutron stars behave as the extreme compact objects theory predicts. Radio pulse timing during eclipses when pulsar signals pass through companion stellar winds or accretion flows reveals dispersion and scattering from ionized material. The timing delays depend on electron density along the propagation path and radio frequency. Modeling these effects requires accounting for orbital geometry, including time dilation and light propagation delays through curved spacetime. Future observations promise improved tests. The square-kilometer array radio telescope under construction will time pulsars with precision approaching 10 nanoseconds for bright millisecond pulsars. This sensitivity enables detecting subtle relativistic effects in binary systems with wide orbits or low masses currently beyond reach. Improved statistics from discovering thousands of new millisecond pulsars will test general relativity through ensemble analyses, Advanced gravitational wave detectors, including the Einstein telescope and Cosmic Explorer, planned for the 2030s, will observe neutron star mergers to higher signal-to-noise ratios than current detectors, enabling precision tests of dynamics during the final orbits and merger when gravitational fields and velocities reach extremes. Observations of post-merger remnants oscillating and collapsing to black holes will probe ultra-dense matter physics. Understanding observational evidence establishes that gravitational time dilation near neutron stars represents measured reality rather than theoretical speculation. Multiple independent techniques using different physical principles and observing different systems all confirm that clocks near neutron stars run slow compared to distant clocks, validating general relativity's predictions in strong field regimes where deviations from Newtonian gravity dominate. Thought experiments. Examining hypothetical scenarios where observers experience the extreme time dilation near neutron stars illuminates the physical implications and helps build intuition for how time's rate depends on position in gravitational fields. These thought experiments, while impossible to perform with current or foreseeable technology, follow directly from general relativity and reveal how radically time can differ for observers at different locations. Consider an astronaut in a spacecraft hovering at rest at the surface of a 1.4 solar mass neutron star with 12-kilometer radius, maintained in position by impossibly powerful rockets providing continuous thrust to counteract the immense gravity. The astronaut's watch ticks at the proper time rate, measuring 1 second per second as experienced locally. Meanwhile, Earth-based observers monitoring the astronaut's signals measure coordinate time according to their distant reference frame. Due to the time dilation factor, A0.809 at the neutron star surface, 1 hour, 3,600 seconds, measured by the astronaut's watch, corresponds to 3,600, 0809, 4,449 seconds, 1.24 hours, measured by Earth clocks. If the astronaut spends what feels like 24 hours near the neutron star, approximately 29.7 hours pass on Earth. The astronaut ages roughly 5.7 hours less than if they had remained on Earth. This time dilation appears reciprocal to the astronaut if they could observe Earth clocks due to light propagation delays and Doppler effects. Earth clocks would appear to run fast during approach and slow during departure. However, unlike special relativity's symmetric time dilation, where each observer sees the other's clock running slow, gravitational time dilation is absolute in the sense that both observers agree the surface clock runs slower once all observational effects are accounted for. Now consider a more extreme scenario. Imagine a hypothetical neutron star configuration at the absolute maximum mass limit, where the surface radius exactly equals the Schwarzschild radius. Such a configuration represents the theoretical boundary between neutron stars and black holes, unstable against collapse but momentarily existing in this limiting case. At this surface, touching the event horizon, where RHRS, the time dilation factor, becomes A(1) RHS equals 0. Time effectively stops from the distant observer's perspective. 1 second measured by the surface astronaut's watch corresponds to infinite coordinate time for distant observers, approaching but never quite reaching the limit where 1 second equals eternity. This matches the claim that near a neutron star, 1 second can equal 1,000 years or more. At RHS, even a tiny proper time interval corresponds to an enormous coordinate time interval. 1 second at the event horizon theoretically equals infinite distant time. So at R(1001 RMRS just above the horizon, 1 second might indeed correspond to thousands of years depending on how close to the limit the position lies. The astronaut at this limiting surface experiences no local peculiarities. Their watch ticks normally, biological processes proceed at normal rates, and physics appears identical to any freely falling reference frame per the equivalence principle. The extreme time dilation manifests only when comparing the astronaut's proper time to distant observers' coordinate time. Light emitted by the astronauts suffers extreme gravitational redshift. A laser pointer emitting green light at 532 nanometers would be detected by distant observers at wavelengths approaching radio frequencies as photons lose energy climbing out of the gravitational well. The redshift factor, 1 plus dis, approaches infinity as the surface approaches the event horizon. Radio signals from the astronaut would arrive at Earth with increasingly longer intervals between pulses, even though transmitted at regular intervals by the astronaut's clock. A 1-second pulse transmitted every second in the astronaut's frame arrives at Earth with spacing approaching infinity as surface radius approaches the Schwarzschild radius. Communication becomes increasingly difficult and eventually impossible. Consider a more practical scenario with two spacecraft, one orbiting a neutron star at safe distance and another descending close to the surface. The orbital spacecraft circles at radius 100 kilometers, where time dilation remains modest, approximately A0.98. The descending spacecraft approaches to 13 kilometers, experiencing A0.79. Both spacecraft synchronize clocks before the descent begins. After the close spacecraft spends 1 week, 604,800 seconds, at 13 kilometer radius, while the orbital craft remains at 100 kilometers, the clocks show different elapsed times. The close spacecraft clock shows 604,800 seconds elapsed. The orbital spacecraft clock shows approximately 604,800 079 0.8781,000 seconds, 9.04 days elapsed. The astronauts aboard the close spacecraft aged approximately 2 days less than their colleagues in the orbital craft during the 1-week period at close approach. This differential aging, while modest compared to special relativity's twin paradox at relativistic velocities, demonstrates gravitational time dilation's physical reality. Now imagine an advanced civilization building a habitat on the neutron star surface, somehow engineering materials and forces to support structures against the enormous gravity. Inhabitants born and raised in this habitat would experience time at the surface rate, perhaps 70% to 80% the rate of people living far from the star. If contact maintained between the surface habitat and a distant space station, the populations would age at different rates. After what feels like 30 years to surface inhabitants, approximately 37 to 43 years would pass for space station inhabitants, depending on exact time dilation factor. Families separated between locations would find themselves aging at measurably different rates. The psychological and social implications would be profound. Surface inhabitants watching videos from the space station would see people moving and speaking 20–30% faster than normal. Space station inhabitants watching surface videos would see everything moving 20–30% slower. Real-time communication would suffer from time dilation in addition to light propagation delays. Children born in the surface habitat would reach adulthood, while their space station-born peers of the same chronological birth date are still teenagers. A person spending a career in the surface habitat might retire after 40 subjective years, while 50 or more years passed for the rest of civilization at large distances. Life insurance and pension calculations would require accounting for time dilation. The economics of such time dilation create interesting scenarios. Interest-bearing accounts would accumulate differently for surface and distant inhabitants. Contracts specifying time periods would need clarification about which reference frame defines the duration. Legal systems would grapple with crimes where suspects claim different amounts of time passed than prosecution alleges based on different reference frames. Education and training take on different character when students and teachers age at different rates. A 4-year undergraduate degree for a surface university student might correspond to 5 years passing for distant family members. Graduate students spending 6 years on dissertations age 6 years personally, while 8 or more years pass externally. These scenarios, while requiring impossible engineering to implement, follow directly from general relativity's well-tested predictions. The time dilation is not science fiction, but established physics confirmed through numerous experiments and observations. The practical barriers involve engineering and survival in extreme environments, not the physics of time dilation itself. The ultimate thought experiment considers communication with a neutron star orbiting civilization from Earth. Radio messages transmitted from Earth arrive at the neutron star surface, redshifted and slowed. A 1-hour transmission from Earth becomes a 1.24-hour reception at the surface for A time 0809. Reply messages transmitted as 1-hour signals arrive at Earth as 48-minute receptions, blue-shifted to higher frequencies. The round-trip communication exhibits a symmetry. Surface inhabitants receive Earth messages slowed and redshifted, while Earth receives surface messages compressed and blue-shifted. Both sides must account for these effects to communicate effectively, requiring careful calibration of transmission and reception systems. Understanding these thought experiments establishes how gravitational time dilation, while primarily manifesting in comparisons between different reference frames rather than local experience, creates genuine physical effects that would affect any civilization or experiment involving strong gravitational fields. The mathematics predicts effects that, while impossible to experience with current technology, follow necessarily from well-confirmed physical laws. Comparison to black holes. Neutron stars represent the most extreme gravitational environments accessible to observation and study, but they fall short of black holes where gravity becomes so intense that even light cannot escape and time dilation becomes infinite at event horizons. Comparing neutron stars to black holes reveals how both objects represent different points on a continuum of gravitational extremes and clarifies the theoretical limits on time dilation achievable in stable configurations. Black holes form when objects collapse to configurations where even degeneracy pressure cannot resist gravity. For electron degeneracy supporting white dwarfs, the Chandrasekhar limit near 1.4 solar masses represents maximum mass. For neutron degeneracy supporting neutron stars, the Tolman-Oppenheimer-Volkoff limit near 2.0 to 2.5 solar masses marks maximum stable mass. Beyond these limits, no known force prevents complete collapse to singularities. The Schwarzschild radius, or TS 16.2 represents the gravitational radius where escape velocity equals light speed. For objects more compact than their Schwarzschild radius, gravity prevents even light from escaping and event horizons form. Neutron stars possess radii REs, allowing light to escape their surfaces, albeit with substantial gravitational redshift. Black holes have all mass within REs, creating event horizons from which nothing escapes. For a 1.4 solar mass object, the Schwarzschild radius equals approximately 4.1 kilometers. A neutron star of this mass has radius approximately 12 kilometers, safely outside its Schwarzschild radius by factor 2.9. A black hole of this mass would have event horizon radius exactly 4.1 kilometers, with all mass compressed inside, likely concentrated at a central singularity according to classical general relativity. The surface time dilation factor for the neutron star equals a Bantio 1 for 1 power 12, 0.809 as calculated previously. At the black hole event horizon, the time dilation factor becomes a Ashta 1 ISSRS, Ashtasho, representing infinite time dilation where proper time intervals become infinitesimal compared to coordinate time intervals measured by distant observers. This infinite time dilation at black hole event horizons creates the appearance that infalling objects freeze at the horizon from external perspectives. Light from objects approaching the horizon becomes increasingly redshifted and arrives at progressively longer intervals, with photons emitted at the horizon requiring infinite time to reach distant observers. The horizon crossing occurs in finite, proper time for infalling observers, but appears to take infinite coordinate time externally. Neutron stars, by contrast, possess no event horizons. Light emitted from their surfaces, while redshifted substantially, reaches distant observers in finite coordinate time. Objects on neutron star surfaces can, in principle, send signals to distant observers, though maintaining position requires enormous forces to counteract gravity. The surface represents an accessible location rather than a causal boundary. The compactness parameter V by 2gm RC2 S2R quantifies how close an object approaches black hole configuration. For black holes, V 12 exactly. For typical neutron stars with M 1.4 m and R 12 kilont, V 0.17. For maximum mass neutron stars with M 2.3 m and R 10 kilometers, V 0.34. The theoretical maximum compactness for stable neutron stars reaches V2 max 0.4 to 0.45 depending on equation of state. The time dilation factor relates to compactness through A 1 to B. For typical neutron stars with V 0.17, A 0.81. For maximum configurations with V 0.40, A 0.63. Only at the black hole limit where V equals 0.5 does A pumper 0, producing infinite time dilation. The relationship between surface time dilation and escape velocity provides another comparison. The escape velocity V c2b equals light speed c when V equals 0.5 at black hole horizons. For typical neutron stars with V 0.17, escape velocity reaches V 0.58 c. For extreme neutron stars with V 0.40, V c approaches light speed but remains subluminal. Photon spheres exist at radius r per ph, Shakti 3gm c2, or to 1.5 RIs, where photons can orbit in unstable circular paths. For black holes, photon spheres lie outside event horizons at r and 1.5 RIs, creating potential for photons to orbit multiple times before escaping or falling in. For a 1.4 solar mass black hole, the photon sphere sits at approximately 6.1 kilometer radius. Neutron stars with radii exceeding photon sphere, radii r 1.5 Rs, have photon spheres outside their surfaces. Photons can orbit neutron stars in unstable circular paths before escaping or impacting the surface. For the 1.4 m example, the photon sphere at 6.1 kilometers lies inside the 12 kilometer surface, so no photon sphere exists outside the star. However, for maximum mass neutron stars with M 2.3 MP, RS 6.8 km, and R 10 km, the photon sphere radius equals 1.56.8, 10.2 km, very close to the surface. Such configurations might support photon spheres just above the surface, allowing photons to orbit in unstable paths grazing the neutron star surface. The innermost stable circular orbit, ISCO, represents the smallest radius where test particles can maintain stable circular orbits. For non-rotating black holes, the ISCO lies at R ISCO, 3 times as 6gm-C2. Inside this radius, no stable orbits exist, and particles necessarily fall into the black hole. For rotating black holes, the ISCO radius depends on spin, reaching as close as RR ISCO, GM C2, SAB 0.5 RRS, for maximally rotating black holes in the prograde direction. Neutron stars support stable orbits down to radii approaching their surfaces if rotation is considered. However, tidal forces become extreme at small radii, destroying extended objects. The Roche limit, the distance at which tidal forces overcome self-gravity of extended bodies, sits at roughly 2 to 3 neutron star radii depending on object densities. Material orbiting inside the Roche limit gets torn apart into rings or accreting debris. Accretion onto black holes versus neutron stars produces different observational signatures. Black hole accretion flows generate radiation primarily from the accretion disk, with material disappearing at the event horizon producing no additional emission. Neutron star accretion creates hotspots where material impacts the solid surface, producing intense X-ray emission, including periodic pulsations, if magnetic fields channel flow to polar regions. The boundary layer, where accreting material transitions from Keplerian orbital motion to the neutron star's rotation, provides additional radiation from neutron stars absent in black holes. This boundary layer emits substantial X-ray flux, contributing perhaps 10–30% of total accretion luminosity. Black holes lack this emission component since material simply vanishes at event horizons. Gravitational wave emissions from compact object mergers differ between black hole and neutron star systems. Binary black hole mergers produce gravitational wave signals dominated by the in-spiral, merger, and ring-down phases where merged remnant oscillates before settling into rotating black hole configuration. The entire process involves vacuum spacetime with no matter contributions. Binary neutron star mergers add matter effects including tidal deformation during in-spiral, possible matter ejection during merger, and post-merger oscillations of hypermassive neutron star remnants before collapse to black holes. The GW170817 observation revealed these features, with in-spiral waveform showing tidal deformability effects and post-merger signals suggesting brief, hypermassive remnant before collapse. The maximum gravitational wave frequency from binary black hole mergers depends only on masses, reaching frequencies where the ISCO orbital frequency occurs. For neutron star mergers, post-merger oscillations of remnants produce gravitational waves at kilohertz frequencies corresponding to fundamental oscillation modes of hot, rotating neutron star matter. These high-frequency signals carry information about dense matter equation of state. Quantum effects near event horizons, including Hawking radiation, distinguish black holes fundamentally from neutron stars. Black holes emit thermal radiation at temperature Th tram C3 Ks 8 pgm Kb inversely proportional to mass. For stellar mass black holes, Hawking temperature reaches only nanokelvins, far below cosmic microwave background temperature. Over timescales exceeding 1067 years, black holes gradually evaporate through Hawking radiation. Neutron stars, having no event horizons, don't emit Hawking radiation. They cool through photon and neutrino emission following standard thermodynamic processes. Young neutron stars emit primarily neutrinos from hot interiors, cooling over years to decades. Older neutron stars radiate thermally from surfaces, cooling over millions to billions of years as thermal energy dissipates. Understanding comparisons between neutron stars and black holes establishes that neutron stars represent the most extreme gravitational environments permitting stable surfaces outside event horizons. While time dilation near neutron stars can be substantial with factors 0.6 to 0.85, only approaching black hole event horizons does time dilation become infinite and proper. Time truly approach zero relative to distant coordinate time. Effects on matter and light. The extreme gravitational fields near neutron stars affect not only time dilation, but also the behavior of matter, radiation, and electromagnetic phenomena through gravitational lensing, frame dragging, photon redshift, and modifications to atomic processes. Understanding these effects reveals how gravity at neutron star strengths influences all physical phenomena, creating observational signatures that confirm the theoretical predictions. Gravitational lensing occurs when light paths bend in curved spacetime near massive objects. For neutron stars, the lensing effect becomes strong enough that photons emitted from the far side of the star can curve around and reach distant observers, making more than half the surface potentially visible simultaneously. This enhances radiation from hotspots and modifies pulse profiles from rotating pulsars. The light bending angle for photons passing at impact parameter b from a mass m equals approximately a 4 gm ounce Bc2 for weak fields. Near neutron star surfaces where gravitational fields become strong, this weak field approximation fails and full general relativistic ray tracing becomes necessary. Photons emitted at large angles from the radial direction can curve dramatically, following trajectories wrapping partially around the star. For photons emitted tangentially from the neutron star surface, the light bending can exceed 90 degrees, allowing photons from the back hemisphere to reach distant equatorial observers. This makes more than 50% of the surface visible, a phenomenon impossible in Newtonian gravity, where exactly half a sphere's surface is visible from any external viewpoint. For the most compact neutron stars, visibility can extend to perhaps 60 to 70% of the total surface area. The gravitational lensing affects pulsar pulse profiles by determining how emission from magnetic polar caps appears to distant observers. The pulse profile depends on viewing geometry, emission beam pattern, and how light curves through the gravitational field. Modeling observed pulse profiles requires full general relativistic ray tracing accounting for light bending, time dilation, and Doppler effects from rotation. NICER observations exploit this lensing to constrain neutron star radii. The pulse profile shape depends sensitively on the MR ratio through its effect on light bending. Hotspots of specific size and temperature on surfaces of different radii produce distinguishable pulse profiles. Comparing observed profiles to general relativistic models constrains the radius for assumed mass, or determines both M and R if multiple hotspots with different patterns appear. Frame dragging, the twisting of space-time by rotating masses, becomes significant near rapidly spinning neutron stars. A rotating mass drags space-time into rotational motion, forcing objects near the star to co-rotate even if they attempt to remain stationary relative to distant stars. The frame dragging angular velocity equals approximately O2 FD 2GJ R3C2, where J represents the neutron star's angular momentum. For a 1.4 m neutron star rotating at 716 Hz, the fastest known pulsar, the angular momentum reaches approximately J 1038 kgm2s. At the surface radius 12 km, frame dragging produces OFD 10 radians second, or roughly 1.6 revolutions per second. Particles attempting to orbit in retrograde direction must have substantial angular momentum to overcome frame dragging, forcing prograde motion. The lens-Thirring precession describes how orbits precess due to frame dragging. For a test particle in orbit at radius r and inclination I relative to the spin axis, the precession rate equals approximately OLT 2GJ R3C2. Binary pulsars with orbital planes misaligned relative to pulsar spin axes show measurable precession from frame dragging, providing tests of general relativity's prediction for space-time dragging. Gravitational redshift of spectral lines from neutron star surfaces provides direct measurement of gravitational potential depth. Atomic transitions occurring at the surface emit photons at specific rest frame wavelengths. These photons lose energy climbing out of the gravitational well, arriving at distant observers with longer wavelengths. The redshift factor 1 plus TZ punch 1 RCHR R 12 can be measured if spectral lines are identified. X-ray bursts from accreting neutron stars create temporarily expanded photospheres with absorption lines from iron and other elements. As photospheres contract during burst decay, absorption lines shift to progressively longer wavelengths due to increasing gravitational redshift. Measuring these shifts determines the MR ratio through Z, constraining neutron star properties. The gravitational redshift affects not just photon wavelengths but also photon arrival rates. A source emitting n photons per second at the neutron star surface appears to emit n1 RRSR photons per second to distant observers due to time dilation. The reduced emission rate combines with individual photon redshift to reduce observed luminosity relative to intrinsic surface emission. Atomic processes, including ionization energies and transition frequencies, technically remain unchanged in strong gravitational fields. The local physics follows the same equations everywhere per the equivalence principle. However, gravitational potential differences create measurable effects when comparing atomic properties at different heights. An atom at the surface versus at altitude h experiences potential difference dF, GH, creating energy difference dE dF, C2e mc2 for mass m. For electron orbitals with effective mass contributions from binding energy, the gravitational potential affects energy levels at approximately dEe dF, C2gr, C2gm, Rc2, of RCRS 2r. For typical neutron stars with Rs 2r 0.17, energy level shifts reach roughly 17% between the surface and infinity, a substantial effect. Spectral lines emitted from the surface show wavelength shifts corresponding to this gravitational potential difference. Particle acceleration in neutron star magnetospheres reaches energies exceeding tera-electron volts through multiple mechanisms. The rotating magnetic field creates electric fields accelerating charged particles to ultra-relativistic energies. These particles emit synchrotron and curvature radiation, producing the radio pulses detected from pulsars and potentially contributing to higher energy emission in X-rays and gamma rays. The intense magnetic fields, reaching 108 to 1011 Tesla, affect atomic structure through Zeeman splitting, where spectral lines split into multiple components in magnetic fields. For the strongest magnetar fields near 1011 Tesla, the magnetic energy scale, EB, MEC, approaches 10 keV, comparable to atomic binding energies. Atoms distort dramatically into elongated shapes aligned with field direction, modifying ionization energies and opacities. Quantum electrodynamic effects become important in ultra-strong magnetic fields exceeding BQED to charge ME2 C3 to E 4.48 109 Tesla. Above this critical field strength, electron Landau levels separate by energies exceeding electron rest mass, and vacuum birefringence creates different refractive indices for light polarized parallel versus perpendicular to the field. Magnetar fields approach or exceed BQED in the strongest cases. The vacuum polarization in strong fields affects photon propagation modes, creating two normal modes with different phase velocities. This vacuum birefringence causes polarization-dependent light speeds, potentially creating observable signatures in pulsar radiation if photon polarization carries information about magnetic field geometry and strength through which the radiation propagated. Pair production, the creation of electron-positron pairs from high-energy photons, becomes enhanced in strong magnetic fields where photons can split into pairs by interacting with the magnetic field itself. The pair production rate depends on photon energy and field strength, with significant production occurring when photons exceed threshold energies around 2 × EC21 MeV, modified by field strength factors. The pair production creates cascades in pulsar magnetospheres where accelerated charged particles emit high-energy photons through curvature radiation. These photons pair-produce, creating more charged particles, which emit more photons, creating avalanches of particles and radiation. These cascades likely contribute to radio and high-energy emission from pulsars, though detailed understanding of magnetosphere physics remains incomplete. Neutrino interactions with matter increase at high densities present in neutron star interiors. While neutrinos interact only weakly with normal density matter, at neutron star core densities approaching 1018 Kg EM3, neutrino mean free paths drop to kilometers or less. Neutrinos become trapped in proto-neutron star cores immediately after supernova core bounce, requiring approximately 10 to 20 seconds to diffuse out. This neutrino trapping affects core cooling and equations of state during the proto-neutron star phase. The trapped neutrinos contribute significant pressure support, making proto-neutron stars larger and hotter than cold neutron stars. As neutrinos escape, the star contracts and cools, settling into its final configuration over tens of seconds to minutes. Understanding effects on matter and light establishes that neutron star gravitational fields affect all physical processes through space-time curvature, time dilation, frame dragging, and photon redshift. These effects create observable signatures in pulsar timing, X-ray spectra, and gravitational waves that confirm theoretical predictions and enable measurements of neutron star properties including masses, radii, and equations of state. Practical impossibilities. While the physics of extreme gravitational time dilation near neutron stars follows rigorously from general relativity's well-tested predictions, the practical barriers to experiencing or exploiting these effects reveal fundamental limitations imposed by the extreme environment surrounding these objects. Understanding what makes neutron star approaches impossible with conceivable technology clarifies the distinction between theoretical possibility and practical feasibility. The tidal forces near neutron star surfaces reach lethal intensities far before an object could approach close enough to experience the most extreme time dilation. Tidal acceleration, the difference in gravitational acceleration across an extended object, equals approximately day times 2 gmh, or r3, where h represents the object's size and r the distance from the neutron star center. For a 2-meter tall human at the surface of a 1.4 m 12-kilometer radius neutron star, the tidal acceleration between head and feet equals approximately da shig 2 6.67 10 11 2.8 2 1.2143 5.4 or 108 ms2. This represents approximately 55 million times Earth's surface gravity. The feet would experience 55 million Gs more acceleration than the head. Such tidal forces would instantly vaporize any biological organism or known material, tearing atoms apart through stress gradients exceeding atomic binding forces. Even at larger distances where time dilation remains modest, tidal forces remain severe. At 100-kilometer altitude, where a 0.98 only 2% time dilation, the tidal force across 2 meters equals approximately 5.41 meters to, or 55,000 Earth gravities, still instantly lethal. Reaching distances where tidal forces become survivable requires moving so far from the neutron star that time dilation becomes negligible. The radiation environment near neutron stars presents another insurmountable barrier. Active pulsars emit intense electromagnetic radiation across wavelengths from radio through gamma rays. The radio emission alone, while seeming benign, reaches intensities of 10^26 watts per square meter per hertz at the neutron star surface, billions of times stronger than radiation levels lethal to biology. X-ray emission from hot neutron star surfaces, whether from residual thermal energy or from accretion, delivers radiation doses measured in terajoules per second per square meter. A spacecraft approaching the surface would absorb energy at rates vaporizing any known material in microseconds. The radiation flux increases as R2 approaching the surface, making closer approaches exponentially more hazardous. Accreting neutron stars in binary systems create even more extreme radiation environments. Material falling onto the surface releases gravitational potential energy, GMM, R per mass m, reaching approximately 0.1 mc2 to 0.2 mc2 for typical neutron stars, 10% to 20% of rest mass energy. This exceeds nuclear fusion's approximately 0.7% efficiency by factors of 15 to 30, creating luminosities that can approach or exceed the Eddington limit where radiation pressure balances gravity. The Eddington luminosity, LL-ED, equal to 4 pgm-mc chi-chi-st, where SST represents the Thomson scattering cross-section, equals approximately 1038 watts for a 1.4 m neutron star. Accreting systems regularly reach substantial fractions of this luminosity, creating radiation fields intense enough to blow away accreting material through radiation pressure if accretion rates exceed critical values. Magnetic fields reaching 108 to 1011 Tesla create additional hazards. Strong magnetic gradients induce enormous forces on conducting materials and ionized matter. The magnetic pressure, B220, reaches approximately 4,024 pascals for B 1011 Tesla, vastly exceeding material strengths of any conceivable substance. Spacecraft entering such fields would experience magnetic forces destroying structural integrity. The particle environment includes ultra-relativistic electrons, positrons, and ions accelerated to energies exceeding tera-electron volts in magnetosphere electric fields. These particles create intense radiation through synchrotron emission and inverse Compton scattering. The particle bombardment would deliver radiation doses measured in hundreds of sieverts per microsecond, billions of times lethal levels, before even considering electromagnetic radiation. The escape velocity approaching light speed at neutron star surfaces creates propulsion requirements beyond any conceivable technology. Hovering at the 12-kilometer surface, where VDESC 0.58c requires continuous thrust, providing acceleration approximately 2 ∗ 10⁻12 ms2 to counteract gravity. For a 1,000 kg spacecraft, this demands thrust force approximately 2 × 1015 newtons. Producing such thrust through rocket propulsion faces fundamental limitations from the rocket equation. dV geschützt VE ln MIMF, where VE represents exhaust velocity and MIMF, the initial to final mass ratio. Achieving hovering requires effective dV comparable to escape velocity, approximately 0.58 c. Even with perfect matter-antimatter annihilation producing exhaust velocity approaching c, the mass ratio must satisfy ln MIMF 0.58, giving MIMF 1.9. This seemingly modest ratio of 1.79 means approximately 44% of initial mass must be propellant. However, this calculation assumes continuous thrust at constant altitude. Reaching the surface from large distance requires additional propellant for deceleration. The total propellant fraction approaches 80–90% of initial mass, even with perfect antimatter engines, marginally feasible in principle, but requiring antimatter production and containment far beyond current capabilities. Alternative propulsion schemes face similar barriers. Solar sails using radiation pressure require impossibly large sail areas to achieve necessary accelerations against neutron star gravity. Ion drives produce thrust too weak by many orders of magnitude. Nuclear pulse propulsion achieves higher thrust, but exhaust velocities remain far below requirements. No currently conceived propulsion technology approaches the capabilities needed for hovering at neutron star surfaces. Even if propulsion hurdles were overcome, structural materials must support themselves against gravity. At the surface, materials experience gravitational stress, S∗GH, where R represents density, G 2 × 10⁻12 ms2 surface gravity, and H object height. For steel with R 8,000 kg M3 and H Wolf 1 meter, the stress equals approximately 1.6 × 1016 pascals, 8 orders of magnitude exceeding steel's tensile strength near 108 pascals. Even exotic materials including carbon nanotubes with tensile strengths approaching 1011 pascals fail by factors exceeding 100,000. No material with atomic structure can support itself against neutron star gravity. The gravitational stress exceeds atomic binding forces. Only degenerate matter supported by quantum degeneracy pressure or nuclear forces can withstand such compression. Time dilation exploitation. For time travel to the future faces additional practical barriers beyond survival. To achieve the extreme 1,000 year per second time dilation requires approaching within infinitesimal distances of the Schwarzschild radius, which for neutron stars lies inside the surface. Even achieving factor of 10 time dilation requires compactness approaching maximum theoretical limits at configuration's edge of stability against black hole collapse. Communication from near-surface positions encounters difficulties from extreme Doppler effects and gravitational redshift. transmissions from the surface reach distant receivers with all frequencies reduced by factors approximately 1 RRSR 12, 0.8 for typical neutron stars. Radio transmissions at gigahertz frequencies arrive at hundreds of megahertz. Visible light becomes infrared. The bandwidth compression by factor 0.8 also reduces information transmission rates proportionally. The round-trip light travel time to neutron star surfaces from safe orbital distances adds communication latency. A spacecraft orbiting at 1,000 km radius for safety would face light travel time approximately 6.7 milliseconds to the surface, creating 13 millisecond round-trip latency. Combined with time dilation, slowing apparent response rates from the surface, real-time communication becomes challenging. The economic and scientific value of experiencing extreme time dilation appears limited given the impossibility of returning useful information or materials to distant observers. Time dilation provides no mechanism for faster-than-light communication or travel. All signal propagation remains limited by light speed in local reference frames. The time travel is only one-directional to the future and provides no advantages over simply waiting. Scientific observations of neutron stars from safe distances using electromagnetic and gravitational wave astronomy provide far more information about these extreme objects than any conceivable close approach. Telescopes can observe neutron stars across the galaxy and beyond, measuring masses, radii, rotation rates, magnetic fields, and equations of state through timing, spectroscopy, and gravitational wave observations without approaching within light years of the objects. Understanding practical impossibilities establishes that while the physics of extreme time dilation near neutron stars follows from well-confirmed theory, the combination of tidal forces, radiation, magnetic fields, and propulsion requirements makes experiencing such time dilation impossible with any conceivable technology. The time dilation remains theoretical curiosity rather than practical phenomenon for human experience.